Okay, so bon appetit, everyone. Thank you for for attending this talk. I will speak about a joint work with Daniel Kane, Shachar Lovet, and Jiepeng Zhang that we did last year in San Diego. Maybe I'll close the door. Thanks. Okay, so please ask questions, as many as you feel, especially if definitions are not clear. Okay, so I will talk about active learning. So let's begin with a short explanation on what active learning is. So in classical passive supervised learning, we have an algorithm that has an access to a pool of labeled examples, and the goal of the algorithm is to learn an unknown concept. In active learning, we assume that the examples are unlabeled, and typically we have maybe a much larger pool of unlabeled examples, and the active learner can interact with a domain expert who can label some of the examples according to the queries the active learner gives the expert. And the goal is to hopefully label very few examples and still to predict as well as the passive learner with access to all of the examples. And this is useful, when unlabeled data is very cheap, but labeling is costly. So for example, maybe in medical applications, where we have data of patients, and the doctor need to label each patient according to the data. So when is it possible? So let's begin with a simple example that shows simple toy example that shows that active learning sometimes is very efficient. So this is threshold in one dimension. So assume that we have n unlabeled points, these black points, and the labels which we don't see are according to some unknown threshold function. So let's assume there is some threshold. To the right of this threshold, everything is plus, and to the left of it, everything is minus. And the goal is to make as few label queries as possible and infer the remaining. And the solution here is very simple. It's just a binary search, right? So what we do is we first query the middle point. Once we see it's positive, we can infer that everything to the right of it is also positive. Then we can query the middle of the remaining points. Say it's negative, we can infer that everything to the left of it is negative, and so on and so forth, until we labeled all points. So we see that using binary search, we only use log n queries, and we infer n labels. Now, unfortunately, this cannot be extended even to the two-dimensional version of threshold functions, namely half-planes. So here is an example that shows why it cannot be. So assume that, so what do I mean by half-planes? Now again, we're given n points in the plane, and they are labeled positively and negatively according to some unknown line that partitions them to two sets. We don't know the line, we don't know the labels. What we can do in each point is to query for one of the labels, whether it's positive or negative. So I claim that here, any active learning algorithm must sometimes ask all the label queries. And the counter example is simple. You just put your point in convex positions, say on a circle. And the observation is that for every point, there is a line which separates it from the other points. And therefore, an adversary can always tell us negative. And as long as you didn't query some point, there's two possible extensions, one in which it's labeled positive and the rest are negative, or everything is negative. So this shows that using just label queries, we cannot do much.
here, it's natural to ask, to get a large fraction right? I mean, I can just declare that they'll all be red and be happy.
You can also show, like in a statistical setting, you can extend this, even if you just care about epsilon fraction, I can find a distribution which is tailored according to this example, and you can still. Okay. So, so we consider an enhancement of the active learner. We want to give it more power, more interaction with the domain expert by allowing it to ask additional queries. Now, it's very important to decide or to understand what kind of additional queries may the active learner use. So perhaps it's very convenient to assume that it can ask the domain expert any yes/no question about the data, and then indeed you will get a very, very strong active learner. And this was explored in the beginning of the 90s, such models, but there were experiments with the algorithms developed in this context that shows that it is useless in practice to allow any yes/no question. And the reason is, I think it's quite intuitive why it's useless, because even assume that it cannot ask any yes/no question, but it can just ask on any point, not necessarily from the endpoints you got, it can ask its label, right? And now assume we have a very high dimensional space, and we have a perfectly separated data, plus and minus, but the data lies on a very, very low dimensional manifold. So the algorithm may just query noise. Yeah, so it will take a positive example, the negative example. It will go to the middle between them. This is a cat, this is a dog, this is the average between a cat and a dog. The human being cannot say anything about which animal it is. So it makes sense to restrict the type of queries that can be used during this interaction. And yeah, so this is we need compatibility with the problem. So one type of additional queries that were explored, okay, this is some related, so there is a lot of related work on what type of queries are possible. Let me give one example of a type of queries that is used in practice. So these are relative queries. So for example, a relative query is which of two restaurants is better, Chez Panisse or McDonald's. Another example of a relative query is, given three objects, which two are most similar to each other. So I will not even try to formally define what a relative query is, but intuitively they are not asking for they're asking for relative information between the points, and not for absolute number. Okay, so these are relative queries, and what we consider is maybe the most simple type of relative queries, which are comparison queries. So let me define formally now what do I mean by comparison queries. So the setting is that we have some hypothesis class, some concept class, and we assume that there is an underlying class, capital F, of real valued functions. On top of it, we take the sign of the underlying class. So for example, if capital F is the class of all affine functions from Rn to R, taking the sign of an affine function gives us half spaces, what we call. If capital F are neural nets without putting the threshold gate on the top node, so capital H will be just the neural net, right? So neural nets are like this. You can think of polynomials. Many well-studied classes are of this form. There is some natural underlying real class. On top we take sign. So a label query is just asking for the sign of the underlying G. And the comparison query asks whether G of xi is greater than or equal than G of xj. Okay? So this is the setting. And we're going to explore mostly when H is half spaces. So capital F are linear functions. So let's see how it already remedies the situation in 2 dimensions. So before in 2 dimensions, we showed if you only need label queries, we need n of them. Now I'll show that we can retain the logarithmic dependence.
So maybe, Shay, another natural thing is to query if g of x is the real value, right?
Yes.
And try to minimize the loss g of x over the data.
But I think this is exactly so I don't know, imagine that whether you like or dislike a restaurant depends on some linear function that happens in your brain, which is how salty the appetizer is, and a linear combination of features. And to ask you for, in the context of classification, to ask you for a number, for an absolute number that expresses how much you enjoy the restaurant, for instance, I don't know if it's a good example, but it's... Yes, so we assume that, but you don't have access to it. That's exactly the point of relative queries. There is some underlying function, or that at least approximates it, but absolute queries asking for the value of the function gives you, is not, the human being doesn't have access to this function, but it can compare, it has a black box access using comparison. So these are the scenarios that...
There's more noise in one model than in the other. Comparisons are more robust than noise.
Yes.
What I said is called active regression, that you have like a real value.
Yes. Yeah, so in other applications you may have such... Okay, so let me now show again a very simple example how we can, in the plane, using comparison queries, we can retain the logarithmic dependence. So an important observation here is that a comparison query between, let's say, 2 red points or 2 blue points, 2 points of the same label, simply compares the distance of the 2 points from the separating line. Right? We have a function f of x. This is the kernel of the function. These are the zeros of the function. It's a linear function. Say f of x1 is 1 and f of x2 is 1000. F of x2 is greater than f of x1 if and only if x1 is closer to the separating line than x2. Right? For linear functions, this is the semantic. Okay, so I'm going to use this interpretation now we can query the distance to the separating hyperplane, which is the same. Okay, so what do we do? So we begin with some unlabeled input of size n and some unknown line. So in each iteration, we sample uniformly at random 10 points. We label all of them. And then using comparisons, we find in each class, we find the nearest point to the separating line. We need just 9 comparisons for that, right? To finding a minimum in an array of n numbers, you need n minus 1.
From the 2 points from each side? Or?
From each side, yeah. So among the red points, I find the nearest one, and among the blue points. And then the observation is that these 2 points need to lie on the boundary of the convex hull of each cluster, so we can consider these 2 cones. And what we can infer now is that all points inside these cones are plus, and all points inside this cone, the negative cone, are minus. This is because these are the nearest points. I will not prove it, but I think it's quite intuitive. So we can just label all of these points, including those that we did not sample, and then just repeat this process on the remaining unlabeled points.
So these 2 points are the 2 points with the lowest margin?
Yes.
So why not take 3 and then just have a slab of unknown?
It's enough to take 2. Yeah. In the plane, it's enough to take 2. So it gives you already, yeah, so.
Could you do somehow binary search on the projective plane? Because, so the gradients are 1.
You are only allowed to pick input points. You cannot ask any point in the plane what is.
No, but a pair of points, so look at the set of the rand square differences. If you arrange them on a circle.
Yes,
you're
I think.
allowed to do binary queries on the circle of the n square.
Yes, I think you can.
So my question is, I guess, is whether it generalizes
No,
3D.
no. Let me get there. Just Yeah, so it's not, for higher dimension, the picture is not so simple.
You're asking if why not 3 instead of 10? Or why not 3 instead of 10?
No, why not, instead of taking the 2 nearest points, take the 3 nearest points or whatever to the margin, to the line. Okay, so the lemma that I will not prove now, but I will prove it on Tuesday, is that on expectation, yes, so the randomness is only the randomness of the 10 points we sampled. On expectation, in each iteration, we infer the labels of half of the remaining points. So, in expectations, it will take us, we have 20 queries in each iteration. In expectation, we have 20 log n queries, and we are done.
But it's improper learning in the sense you don't get a hyperplane, you get something else. Basically what I showed you now, just how to infer the labels of all the data sets. Once you infer it, you can give it to an ERM, and then it can be proper also.
The 3 points you always maintain.
Yes.
Okay, now let's discuss higher dimensions. So first of all, for the 3-dimensional space, we have some bad news. So there are again data sets. There is a set of endpoints such that every algorithm with comparison and label queries requires n over 2 of them. So this is bad news. By the way, one interesting question here that I don't even know how to formalize is that we saw that in 1-dimensional label queries suffice, but for 2-dimension not. In 2 dimensions, we take something like we have a query that is a comparison. It's between 2 points, and this solves the 2-dimensional case. Maybe for a 3-dimensional case, there is something that involves 3 points, and we'll solve this, and so on and so forth. Maybe there is like kind of a, but yeah, just for imagination. Okay, so what are the good news? So first of all, these counterexamples are very exotic. Now, what do I mean by exotic? Is that we can do much better when the data is nice. So for example, if each data point has bounded bit complexity, by which I mean that these are bounded integral vectors, integer vectors with bounded coefficients, or there is a large margin, but we will see that the margin can be very, very small, in fact, just non-trivial margin, then you can do much, much better. So for example, so if we assume that each point, each of the, we have n points. Each of the point is vector of integral coefficients with some upper bound b. Okay? So we can retain the logarithmic dependence. We can do it in d log b log n.
How much would you use in standard
You need all of them. Okay, so let's consider an example. Let's take let's assume that the data set is all 2 to the d points in the Boolean cube, all 0, 1 vectors. So these points are in convex position, and therefore the same argument like in the plane shows you that any active learning algorithm needs to ask all 2 to the d labels. What we show is that you can do it in just d squared labels. You can infer everything. So d squared, no labels and comparison queries.
For a hyperplane?
Yes, so there's some unknown linear function, some threshold functions over the reals. You have the 2 to the d hypercube. You have a query access to the linear function either by comparison or by labels, and you can do it in d squared.
And this is tight.
And this is tight. This is tight. Well, that's correct. So up to this tilde it's tight. Yeah. But and by the way, this is closely related to the subset sum question, right? If you think about it, think of the normal to the unknown hyperplane as an input array. So what does it mean that we find all labels of 0, 1 to the d? We just have the inner product of all binary vectors with the input array. So every subset of the input array, we classify it either as negatively labeled or positively, So this relates to what I'll do on Tuesday in the IIS.
Why is this tight?
Because each question is a yes/no question. Each query is a yes/no query. How many? So the number of how many partitions of 0, 1 to the d you have by hyperplanes, by linear functions?
you have 2 to the d squared, 2 to the d to the d, right? You have, if you have n points in Rd, you have n to the d partitions. And so it's just the information theoretical lower bound. Okay, so that's just an example why it's non-trivial. Okay, and also for margin we have a result. So assume that now we have a set of points in Rd. Now they are arbitrary. They can have very, very weird coefficients. But assume that, you know, the separating hyperplane has a large margin with respect to these points. Then you can do d log 1 over the margin log n. And this dependence, I didn't know such dependence on margin, but it turns out that Tomer told me that.
Linear programming gives you this dependence on margin.
So you mean like cutting planes, or not linear programming? Linear programming?
Because binary classification is equivalent in the realizable cases.
Yeah, I understand. But which algorithm, which optimization algorithm gives you such dependence on the margin? Yes. So these cutting planes, yes. Yeah. So with so I'm used to, you know, to 1 over gamma squared with no dependence on dimension. The idea of margin is to be independent of the dimension. You have but anyways, so it gives a similar dependence like
There is actually no algorithm that is independent of the margin at all.
No, the perceptron, right? Or
No.
On the dimension, it's.
This is a strongly, there is some conjecture, I forget. Strongly polynomial algorithm for linear programming. It's equivalent to this.
Okay. I see. Okay, so yeah, but as I said, the whole idea of margin, or one of the main ideas of margin, is to get rid of the dimension dependence, and this, unfortunately, we cannot do. So, so again, there is a sample of n points in Rn plus 1, non-constant dimensional space. The margin is 1/2, but still, any active learning algorithm must use an omega of n queries.
The mean depends on the busy dimension of the part.
Yeah, so the V's dimension here will be constant, right? Because the margin is large.
Oh, okay. And yet you see.
So the computational complexity of your method must be large polynomial in dimension.
It depends. Yeah, I think so. I mean, already the threshold function on the binary cube, I suggested that it's equivalent to subset sum. We cannot expect to solve subset sum in polynomial time. Okay, so now let me talk about, so really all these theorems, all of these examples are just application of, there is a simple definition that captures the query complexity here, and then each theorem I showed you is just analyzing the dimension of the particular problem.
Quick comment about the right query about triplets, I think, is you're given 3 points and you're being asked, so it induces a plane, and you're being asked whether the gradient is in this direction or in this direction. So which one is the positive direction? I think that's the right generalization that would give you.
You think this will give you logarithmic dependence?
Yeah, I'm not sure if it makes any sense for
it's
classification, but basically for 3 points. So for 2 points, the gradient is just which one is bigger. For 3 points, is the inner product with the gradient positive in this direction or that direction?
Sounds interesting, yeah? Maybe.
And because, then you can do binary search on triplets. Basically, I can always find a trip,
Sounds interesting.
Or generally ellipsoid. It's a cutting plane.
Anyway. But it probably doesn't make sense in this context.
No, it makes sense to me. Perfect sense. Okay, so I want now to define a very simple combinatorial dimension that enables all of this analysis. Okay? So again, it's a combinatorial dimension that captures query complexity. It reduces all these statements about query complexity to very concrete mathematical statements that are very, on the table. And it also extends to any type of local additional queries. So if instead of doing these comparison queries, you do whatever Mark suggested, or the three-wise comparison, then still you will have an inference dimension for this particular setting, which will still capture. So it's really, you can use it to any extension of this model of comparison queries. So what is the inference dimension? So this is the only maybe technical part of this talk. So again, we have this class H, which is a sign of F. F is a class of real function. The inference dimension of capital H of this class is the minimal number k such that every realizable sample of size k, every sample that, and there is some target function from the class that labels this sample, every realizable sample of size k contains some point in the sample that we can remove this point, ask all labels and all comparisons on remaining k-1 points, and infer from it the extra label. So you don't need to be able to tell me which point it is in advance, but God knows, for every realizable sample of size k, there is a point that you can remove it, ask all labels, all comparisons, and infer.
It means that you can always infer from k-1, you can get everything.
Not really. Not really. But
Does it imply that?
no, because you have comparison queries also. I mean, it doesn't imply it. Let's see two examples.
You don't know which point.
There is a set of k-1 that would imply all the others.
But the point depends on the k.
So let's see one example in what we said holds, and then see another example where it doesn't hold. So I claim that the inference dimension of one-dimensional thresholds is 3. What do I need to show you? Is at most 3, I'm sorry. I need to show you that for every realizable sample of size 3, there is some point that if I remove it, I can infer its label from the remaining guys. So there are two cases. If the 3 points have the same label, so I see the label, then I can remove this point. I can remove the label of this point. I can hide it from you. And since any threshold must have at most one sign change, you know that this guy must be labeled positively. Okay? And if they have distinct labels, different labels, then one of the endpoints can be inferred for the very same reason that there cannot be two sign changes. Yes?
This definition you also applied to signs of neural networks or other classifiers or only linear classifiers?
No, it applies to anything, any concept class, anything. Okay, so this shows that the inference dimension of thresholds on the line is at most 3. And here indeed what they have said is true, because notice that we only used label queries here. There was no comparison query. So this also correlates with the fact that there is this binary search with only label queries. We didn't need comparison queries, you see? So the inference dimension only with respect to label queries is 3. Okay. Now I want to claim that the inference dimension of half planes is at most 7, and it is in fact 5. But we will see why it is at most 7. So again, given any realizable sample by 7 points, I need to show you some point there that can be inferred. So the first observation is that there must be 4 points with the same label. Okay? And then we do exactly like this algorithm that we saw. Using comparison query, we find this guy, the guy that is closest to the separating line, and then again we consider this cone. We connect it with its two neighbors on the convex, on the boundary with the convex hull, and extend it to a cone. And the remaining point must be inferred. So this guy I can remove. Right? I know that anything in this cone is positive. And here you cannot do. So here, I mean, okay.
But if you had 20 points, you can always reduce it to 6. Just pick one and throw it out, right? And then keep doing it. At every point you can recover what you lost.
So the labels yes. Actually we use it, yeah. Okay, now I understand what you meant. Yes. Yeah, so what they have said is that if you have k plus m points, so you know you can. No. No. You confused me, but no.
I mean, the next point you want to find the label of maybe need that.
Listen.
Its label maybe needed.
Not only, listen, you remove 1 point. You're right. I have now 20k points. I can remove 1 point and infer it. But maybe I inferred it after I sorted everything else. So you sorted everything else and you have the labels of everything else. Now once you remove another point, you don't know where it's positioned. You just know you can find its labels, but you also need maybe to find its position in the sorted.
So here you don't have to find the position,
just the label. Yeah. You only care about the labels. Okay? So is the definition clear? That's the important. Okay, so now everything boils down to analyzing the inference dimension of the relevant classes. So, here is a nice exercise. Consider the class of univariate polynomials of degree at most d. What is the inference dimension of this class? Okay? But as I said, everything now boils down to analyzing the inference dimension. So, sorry. Yes, why does it boil down? So, as I said, the inference dimension captures query complexity. So, in particular, if H has inference dimension k, and it can be neural nets, it can be any class you want. If it has the inference dimension k, then there is a very simple algorithm that finds it in k log n. And k log k comes from the fact that in each iteration we sample 2k points, we sort them, this is k log k queries, and we ask the labels, and we infer. That's it. It's the same algorithm we had before.
Deterministic algorithms, you have lower bounds points.
We can, in some cases, for half spaces, you can de-randomize it, this algorithm. So we didn't consider other cases.
Okay, it's possible that for every problem you have a deterministic algorithm?
Yeah, I don't know. Maybe.
But you need to be able to infer, right? To actually efficiently do the algorithm?
Yeah, inference is a bottleneck, or computational bottleneck, indeed. The inference part. Yes. Yes, and there is also a lower bound. If the inference dimension is more than k, then you need, for some distributions, for some samples, you need more than k queries. And the algorithm is very simple. In each iteration, we sample 2k points, we query, we apply this inference. This inference part, by the way, is just solving a bunch of linear programs. So actually, maybe it can be efficient if you use this. So inference is, you just solve a large number of linear programs. You can reduce it to that. So I'm not sure, actually, it's a bottleneck.
For half spaces, not in general.
For half spaces, right, for half spaces. Okay.
So inference dimension captures queries of labels and comparisons, not other.
Yeah, so for every type of additional queries, there will be an inference dimension for this type that will capture the query complexity for this type of.
So it can be any Boolean function on the.
It should be the arity should be small. So comparison queries just ask about 2 points, right?
Okay, so the arity comes
Yeah.
into the.
Yeah. I need to think if it can be extended, but yeah. We use arity, small arity.
Do you have any relationship known between this and this dimension? Can be arbitrary?
So we already showed that in R3, we had this counter example in R3. R3, the inference dimension for comparison queries is infinity, and this dimension is 4.
Sorry, I guess they asked that, can we know what is the point that can be inferred?
No. But we don't use it also in the algorithm. The algorithm just samples 2k points. Yeah. It sorts them and has the labels of all of them, and then it infers. This is now a very.
But we don't know which points can be inferred.
Yeah.
Hyperplane you do know.
So this is just for hyperplane?
No.
No.
In some problems you would know the class of functions.
Okay, but I know that if the inference dimension is low, then you have an algorithm.
Yeah.
For
You have a meta algorithm. You have a meta algorithm. If the inference dimension is known, then this is the meta algorithm. You know that the inference dimension is k, the algorithm should know it, and it should also know how to infer, whatever this means for half spaces. We saw some examples.
If you have a routine for inferring, then
Yes.
But how do you show it?
By the way, the proofs are really, really not complicated, and I will give them on Tuesday. It will take me, the proofs will probably take me just 20 minutes. It's really not complicated proofs.
So here is where you
Just show existence.
so here is where require k square is 2.
k log k. If you have any, so for sorting, you have the nice thing that you can infer all k choose 2 comparisons using just k log k. Yeah, in general, if you have arity.
In general, if I take this meta algorithm, the number of comparison can be
Yes.
can have k square.
Yes.
What is query them label plus comparison?
Yeah, so you query them, meaning you
Just all the
you ask all the labels, you find for each one of these 2k points which one is positive, which one is negative,
and all the relations between them?
and then you just sort. You sort each class like we did before. You take all positive points, and you find the one that is nearest to the hyperplane, the one that is second nearest, and so on and so forth. And you do the same thing for the negative points. And then comes this abstract step of inference. So whatever you can infer mathematically, you infer.
So this generalizes the protocol for hyperplanes?
Yeah.
So this, the same thing we've done for hyperplanes can be done for anything with
Yeah.
inference.
Yes.
The professor says something like that for every k tuple, there are many k tuples where you hit k minus 1, that you kind of can infer at least one more point, right?
It's too bad you won't come on Tuesday. Because it's not, but we can...
The only thing you can do, right?
No, we do something simpler than this. Okay.
It's true that in general, I can find k points and I can query k minus 1 of them, and I won't be able to infer the last one, right? Because it can, sometimes I needed a different.
Right, definitely. It's a statistical statement, right? It's a typical...
So, but the complexity then is just a function of k, no matter what it is.
No, log n, I mean, you have the batch, the input sample is of size n. And in each iteration, half of them are inferred. So you need log n.
About the inference of a label of a point. You will make an inference about the constant fraction. But the inference routine you do
Yes.
is just inferring the label of a given point
Yes.
that you didn't label before, or you didn't ask for, from the ones you know. The complexity of this problem is a function of k.
Right.
So even if it's an anti-hard problem,
Right.
the first dimension is small, then it's a
Yes.
stick.
Yes, potentially, yes. Yeah.
Makes a difference if this complexity depends on n or depends on k.
Right.
Or maybe inferring, it also depends on the set that you're...
No. You just ask whether this, you 2k actually, but never mind. You take these 2k guys, you label all of them, and then you take a certain other point, and you ask, can I infer its label? So the input of this algorithm is this 2k points plus 1. And the underlying structure or whatever, but... Okay.
Also, in the like induction step or whatever, you only infer labels, you don't infer comparison values. So,
You already have an induction.
well, I mean, you're gonna start with 2k points and then you're gonna keep going, right? Or you're not gonna use the.
What we have to prove is that there exists a constant fraction, each of which is inferred from the sample.
I see, and then you don't use those for future inference at all.
No. It's a you can forget in each iteration everything. Okay, so so for the case of bounded bit complexity, so assume now H is the class where X is this thing, 0, 1 up to B to the D, and H is all the dimensional half spaces, then the inference dimension is D log B. And this gives us the result from before. And by the way, so we used exactly this theorem, and this is what I will talk about on Tuesday, to show that there is for every n, there is a comparison-based algorithm for k-sum that uses n log square n queries. and k times n times log. Anyways, for k equals 3, 3 sum, yeah? Take 3 sum. It's conjecture that you cannot do it better than n squared. This is a conjecture from 95. But if you consider a non-uniform comparison-based algorithm, then you can solve 3 sum in just n log n, with just n log n comparisons. So you, in each point, you either take a subarray of size 3 and you ask, is the sum 0? Or you take 2 subarrays of size 3 and compare their sum. Right? So it's very different from merge sort that is, like also for sorting we need n log n comparison queries, but this is tight also. Yeah.
So back to actually Avi's question, I think this is a good point. I mean, you cannot expect then this dimensionality you have for neural net or for hard things to be finite. It's going to be an infinite dimension.
I think it really depends on the context. Like you see here, we really tailored x to be integral vectors of bounded norm. So if instead I would take d3 and x is an arbitrary, is all R3, then it would be infinite. So this inference dimension is small, really depending on both x and h. So if you take h neural nets and x is unrestricted, then of course you cannot say anything. It will be infinite very, very fast.
But even this, even 0, 1, 0,
I don't know. I don't know.
I will resolve this one. I mean, it's an NP-hard.
No, but just because the inference dimension is small doesn't mean you can infer, right? You can't
It
ask
means
about
you have an efficient algorithm.
No.
If I give you a neighborhood of k points and I give you a neighborhood, can you say if a neural net must label it this way or that? You can.
You can take, you have an algorithm that basically infers everything, the leveling of everything.
How do you know if a neural network label A and B as positive, must it label C as positive? You can't solve it.
No, that's what I'm saying. So the inference dimension must be very large.
No, just because you can, I mean, the efficient inference dimension can be large.
More than
Efficiently
It's
infer.
the same. It's the same dimensionality, right? It's the efficient inference dimension and the same.
If we would know what is the difference.
It has to be bigger than the number of parameters in the model, right? Because that's like the dimension.
You need to go all the models and check. Does this infer this? You cannot check it efficiently. Even if it's small. You cannot verify it.
No, if the
I mean, what Avi said is that the inference step does not depend on n. It depends on k and the extra point and on whatever the algorithm did before, which may be hard, maybe not hard. It depends on the context.
what happens before?
So it depends. I mean, not on the algorithm, on the problem itself, on the setting of the problem. So.
For example, here it will depend on the depth and the size of the neural network, right? So it could go to infinity as the size goes to infinity or something.
I'm saying it must. So like if you have label queries and comparison queries, which you do have, right, for given data, then you must expect this inference dimension to be, cannot be very small for neural nets. If it is small, you could have.
Yes,
Be the size of the neural network. Right?
Yes.
It can be smaller than the number of parameters in the network. I mean, but ideally it would be comparable to the number of weights in the network, and then you could learn from that.
That's another question. So,
Sure.
in response to Roy's comment, the algorithm explicitly said, take these 2k, infer everything that you can infer. It's not obvious that this can be done in polytime for neural networks, right?
Right.
So just because it has, if it happened to have low inference dimension, it would not necessarily imply a polytime algorithm.
Yeah. Yes. I didn't think at all about neural nets in this context, but it's plausible. What you're saying is right.
How is this result related to my afterlife or this one? I mean,
Okay, so yeah, what Meyer of der Heide and Clarkson, all of these guys, they actually, in the language of learning people, they said they consider the problem of, you have again, half spaces, but now you're allowed to ask any membership query. So you can take any point. There is some separating hyperplane, which you don't know what it is. You can take you have n data points. You need to know all the labels of the n data points. But now you can ask any point in the space, whether it's on the positive or the negative side. And yes, so it has been known since the 80s or the 90s that this you can do in times poly d log n.
Time is the decision tree. It's
Yeah,
non-uniform
yes.
model is just-
Yeah, non-uniform model in number of queries is poly d log n, which is quite surprising because it includes.
NPR.
Yeah, it's NP hard and what we showed is that for some nice data sets, so if your points are nice, like here, then you can take it to the information theoretical lower bound d log n. But and we have now actually we try to generalize it for arbitrary data sets, but yeah, some other time. Okay. So we have a similar result for margin. Yeah, it's the same thing, right? You want to analyze the query complexity, you just analyze the inference dimension. I will not even.
Is it clear how the application is an application here?
Is it clear how the application? No, but hopefully on Tuesday it will be clear.
It's not. Here you have the queries themselves are hyperplanes or something. Before you have comparison.
So the algorithm is this algorithm. So we just assume that the inference dimension is k, and then we sample these 2k points. And
Comparison can be implemented by can you go to the slide with the application?
which one?
Is it this one? Yeah. So you have.
So again, it's a non-uniform algorithm. We just show that for every fixed n, there is some comparison-based algorithm. There is a linear comparison decision tree of relatively small depth. It's not that there is an algorithm that for every n. So it's a non-uniform complexity. Okay. So let me suggest now a little bit of future research. So yeah, extend it to other type of relative queries, your favorite. Now, in the beginning I said that membership queries were considered by theoretical machine learning, but were left out because it has been shown that it's not practical to query, because the space in which you represent your data, not every point there will make sense to the human being. But now maybe when we have these, generative models like GANs, maybe we can use them to generate meaningful membership queries, right? So now we can train a GAN, and then we can feed to this GAN noise, and it will generate us presumably a meaningful membership query. So maybe we can utilize these generative models and justify again why theoretically it's worth studying these membership queries. Online models, I think it's also, now instead of a batch of unlabeled examples, you get a sequence, and you want to do the same thing. Agnostic setting, noisy comparisons, and other,
You have an example where the VC dimension is large but the inference?
You can cook such examples. It's,
Natural?
I remember I convinced myself I can cook such example, but we can, natural, no. Natural won't be. You just kind of want to encode you want to take it like shattered sets and then add the tail, and in the comparisons on the tail, you can basically infer everything. That's kind of the idea. Like you can identify it. Anyways, we can do it over coffee.
So you started working on the noisy case?
No, and then on the noisy comparisons.
So there are two noise modes. One where there is just one edge that is noisy, one comparison. The other one is that you have a label noise there for all the
Right.
A-1 comparisons.
So
one is easy because they define inconsistency. You can may be able to reduce it to a no-noisy case, but it's not realistic.
So we consider the model in which the adversary may lie at most k times, at most p times, some
Edges, not on comparison.
on anything, and yes, but it's actually not really in learning this work. It's more like 20 question games with lies. So, but maybe later we can think what it means for learning. But it's just a combinatorial. Yeah, should be done, huh?
It starts. Saying that I'm Tuesday.
No, but it won't be on.
And it's only 20 minutes.
No, Tuesday is 2 hours. Don't hope. Yeah. Yes, and also other applications of the inference dimension. I don't know. It would be cool to have some. I mean, at least the VC dimension had many applications in outside machine learning. Yes, so that's it. Thank you.